All right, I'm Mr. Sand, and now we're going to do acceleration graph. This is topic 3 in Unit 2, acceleration. Now, oftentimes this is a difficult subject for students. And the reason is it's just hard to visualize. Because what you've been doing so far, you've taken a distance, or this should actually say position. So this is wrong on here. This should say position. So I'm going to change it right now. Wow, this is crazy. So this should say position. Give me that. Position. Right. Okay. So you go from a position versus time graph to a velocity versus time graph. And to do that, you needed to look at the slope all the way around here and translate that into velocity. Now you're going to do something from this graph. You're going to take this graph and find the slope of it. So really, you're finding the change of velocity, and that's going to be your acceleration versus time graph. So you're finding, oh, this is great. You're going to love this. The change of position. So the change of position over time is velocity. The change of velocity over time is acceleration. And to find the change of something using this graph, which is the position over time graph right here, to find the change of this over this, you find the slope. And here you're going to find the slope, and here you're going to, well, I guess you don't have any further change of acceleration, but it's actually true that you can find the change of acceleration if you want to. The technical term is jerk. So here we go. Let's go through this little kind of diagram here. It really helps to kind of figure out what's going on. So at first, I'm going to read this little bubble. It says increasing slope indicates what about the velocity? Think about that. If you have an increasing slope, does that mean what happens to the velocity? The velocity is an increasing velocity here. It's increasing. So the slope here, it was, let's use a different color. It was, turquoise. It was like this at that point. At this point right here, it was like this. At this point, it is getting bigger, and it's getting bigger and bigger. So it's increasing. An increasing slope means an increasing velocity. Okay, different color. I don't like that color. Let's use fern. At this point, a constant slope means what? So at this point, this is a slope that is not changing. So that means a constant velocity as well. A constant slope means a constant velocity. Right here, a decreasing slope indicates what? So let's use a different color again. Let's use ocean. Here, the slope is like this. Here, the slope is like this. Here, the slope is like this. It's slightly changing. It's becoming less and less. So that means that the velocity is also becoming less and less. A decreasing slope indicates decreasing velocity. Right here, a horizontal point, zero slope, indicates what? At this point, if something has a zero slope, it is a zero. I'll just put the numeral 0 velocity. A negative slope indicates what? Just the fact that it is negative indicates that the velocity is also negative. All right, let's use a different color now. Use eggplant. Flattening curve implies velocity becoming less. So here we go. This curve, the slope was here. Now the slope is here. Now the slope is here. Now the slope is here. You can see that the slope is changing. It was negative. Now it's less negative, becoming less negative. Continuing with 0, slope implies the object is at rest. That's great. That whole statement's fantastic. All right. Now let's go to this graph over here. It says positive slope implies what about the acceleration? Positive slope right here. So remember, the acceleration is just the slope of the velocity versus time graph. So the positive slope here means a positive acceleration. So I'll use a different color. Cayenne. Positive acceleration. And a horizontal line, zero slope implies, well, the slope here, since the acceleration is just the slope of this line, it should be a zero acceleration. And a negative slope implies a negative acceleration because this slope right here is negative. It's all about the slope. The slope is the acceleration, so it makes sense that these should be the same. I want to take a look at the shape of these graphs now. Here you can see that the slope is right here at this point. That's 0. So at that point it was 0. Here it's becoming a little bit more. So here it's a little bit more. Here it's even more. So it's even more here. The velocity is getting higher and higher and higher. So with this curved shape, that means that the slope is continuously changing. And here the slope is, that is the graph of the slope. So it is continuously changing to be positive. When this is a straight line, this should be, the velocity should be a constant value, meaning that the slope is a constant value. When this is decreasing, it looks like the slope is continuously decreasing, it's decreasing, it's decreasing, it's decreasing. This line should be negative, and it is. It's going down. Every point along here, the slope is becoming more and more and more. It's decreasing, it's decreasing, it's decreasing. At here, at this point, this is a critical point. When it's 0, the velocity should be 0, and it is. And then when it goes negative, when the slope becomes negative, this velocity versus time graph should show that it's negative, and it is. At this point right here, this is a great point right here, because the flattening curve implies becoming less and less negative. So this slope is becoming less and less of a negative number, and here it's becoming less and less of a negative number. When it's flat, this should be flat as well. Now, if you take a look at the acceleration versus velocity graphs, the acceleration versus time graph and the velocity versus time graph, you can translate this graph into this graph down below. The way you do that is just by simply looking at the slope and translating the slope into the acceleration. So here the slope was at 4, and so this acceleration was 4 this entire time. Then the velocity just snaps off and becomes 0. The slope of the velocity, I should say. The velocity itself stays constant, but the slope of the velocity is 0. So the acceleration then is 0. The change in the velocity, it didn't change, so the acceleration is 0. That should make sense. Here, it is constantly changing. So this acceleration versus time graph should be a constant number. And it is. It's a negative number. You can line all of these up, and now at this point right here, the velocity is now, the slope is positive, and so this should be positive as well. This should all make sense to you. Review this over and over again, because it really, really brings home the point and how to translate the different graphs into each other. Now I'm going to give you a couple problems. Let's see how my time is doing here. In a position versus time graph, a positive slope to the graph's line means what? What is a positive slope? It means a positive velocity. We don't know what it means about its acceleration, because it doesn't describe anything else besides that. That is very messy, but it says positive velocity. In a velocity versus time graph, a negative slope to the graph's line means what? In a velocity versus time graph, a negative slope to the graph's line means what? It means a negative acceleration. It's just asking you, well, a slope in a velocity versus time graph just is the acceleration, so it must mean it's a negative acceleration. Now let's go on to the next problem. I'm going to use a different color. I'm not a fan of cayenne. I'm going to use clover. Imagine Mayor Bloomberg flies away in his helicopter at the same height for 11 seconds. From 0 to 2 seconds, his velocity changes from 0 to 10 meters per second. Okay, so let's just say that Crap. I think I'm running out of time, so I'm going to stop it right there, and I'm going to finish number 3 on a different video because it's going to take a little longer. Okay, bye.